I'd like to welcome you to the banquet and to the program that we're going to have here. We're going to begin by giving out awards to a number of people who have certainly earned them. Then there will be a short presentation by one of the people who won an award, and then the full banquet presentation by Steve Squyres, who won the Mars Pioneer Award for this year, which is our most prestigious award. And then he will give a talk and take questions, and then after that I will give a talk. So for our first award for this year, the Deputy Director of our Education Task Force and an all-around terrific guy, Chuck McMurray. Sorry. And this is for outstanding service and dedication from September 2012 to August 2013. All right, there you go.
Thank you, Howard.
Thank you.
Appreciate it.
Our next award is for Nicole Willett, okay, who is the Education Director of the Mars Society. These two are a great team. Some of you may have seen the youth education, the STEM education event that we had going on next door today. It was terrific, and this was Nicole's brainchild, along with Chuck and, of course, also Hope. Have to say Nicole's been out there, has been over the top. She also had a great article recently in an astronomy magazine about the Mars Society. It's like an 8-page article. It's fantastic. Okay. Anyway, Nicole, congratulations.
Thank you very much.
Our next award is to a founding member of the Mars Society, and who has been with us, well, since then, and intensively so, especially in helping to make the Mars Desert Research Station a success. So this is an award that he's earned for really 15 years of dedicated service to the Mars Society in general and the Mars Desert Station in particular. This is for John Baranka. Our next award goes to Joe Pillea for tenacity and achievement in leading the Mars Arctic 365 Phase 1 mission. Joe's going to give a short talk right now, but I just want to make a few comments. This year's mission was a tough mission. I can't go through all the details, but we had a situation up there that could have turned bad, and Joe saved it. Joe saved the mission. There were a lot of people backing him up. I backed him up. Susan backed him up. Jill backed him up. There were people up there with him. But I have to say, if there was one person who made, you know, this year's mission a success instead of a failure, who made the difference, it was Joe. And so you really showed you had the stuff, Joe. So congratulations.
Thank you so much, Bob. It means a lot to me. I really enjoy doing the FMARS program, and I appreciate your recognition of what I've done. Okay, so without further ado, I'm actually going to tell you guys a little bit about the mission, some of the things that happened, not everything, but the highlights at least, and talk about the larger Mars Arctic 365 program in general. So first, a little bit about myself. So I served as the field season director and the crew commander for the expedition this summer. I'm planning on going up and leading the refit mission, the second refit mission, next summer before the one-year crew comes in, provided Bob will allow me to continue to serve in that manner. A little bit about myself. I consider myself an entrepreneur. I have a lot of startup experience. Pretty much my whole career has been focused on aerospace startups. Trained as an engineer. I have a bachelor's degree in electrical engineering, master's degree in nuclear engineering, and I consider myself a leader. I like leading teams. I like working in a program management type of role. And the focus of my life has always been to help further the human exploration and settlement of Mars. So I'm very happy to be working with the Mars Society towards that end. Right now, my current employment, my day job, is with a company called Earthrise Space. It's the Omega Envoy team competing in the Google Lunar X Prize. Although actually I'm looking to make a move, hopefully in the near term, and focus a little bit on where my passion lies. Going to the moon is nice, but it's nothing compared to Mars. So I am available for work if. Before I worked for Earthrise Space, I was the vice president of another startup company called Four Frontiers Corporation, and we did 2 design studies of what a initial permanent Mars settlement would be like, what would the infrastructure needs be, and how would you build such a settlement. And in terms of what I've done with the Mars Society, I actually first read the Case for Mars when I was an undergrad, and as I think many, if not all of the people in this room, I was inspired by that. And really led a direction for my life. I was part of the MIT chapter of the Mars Society while I was at MIT, working on my grad work. Attended many conventions, and then in '09, I was selected, along with a number of fellow crew members that put in an application together, to take part in the '09 FMARS expedition. So this summer's expedition was actually my second trip to the station. So what is Mars Arctic 365? Quite simply, it is going to be a groundbreaking Mars simulation in the Canadian Arctic. It's going to do all the things that we've done in previous Mars simulations at MDRS or at FMARS, but it's going to take it to a whole new level. It's really going to prove that we can take a team of dedicated individuals, put them in a harsh environment, give them a set of tasks to do, and we're going to see them succeed by working as a team and overcoming those challenges together, just as the first human crew on Mars is going to have to do. This really, I feel, will be the most realistic Mars simulation in history. For those of you who are not familiar with the FMARS program and where FMARS is, there's a map there so you can see it's pretty much as far north as you can go on commercial airliners, and then you have to charter a bush plane to take you even further into the Arctic to get to Devon Island, where the station is deployed. It's a Mars analog site. It has certain characteristics. For instance, it can get very cold in the winter, down to about -40. It's very remote. It's about 1,000 miles from the North Pole. And it's the site of an impact crater, the Hawking Crater. So this is shock terrain. There's very little vegetation since you're so far north. It's a good Mars analog site. What I really like about it is that it forces you to think like a Martian, because you have to go through this long, arduous journey to get there in the first place. It's very expensive and difficult to get supplies and equipment on site. If something breaks, you can't just run to the corner hardware store or the local Home Depot because they're thousands of miles away from you. So you really have to improvise. You have to work together as a team with the limited set of supplies and equipment that you have to overcome whatever challenge you're facing. It's not something that you're going to get from trying to do a simulation in the backyard at JSC, where you could just run back into the lab or you can run down to the corner hardware store. Why is this important? Why is this mission important? Because it's never been done before. Past FMARS expeditions have ranged from anywhere between a couple of days, a week long, a month long, to I think it was 4 months in 2007. But a crew has never spent a full year at the station, including wintering over. Now, if you look at beyond just FMARS and maybe what we do with MDRS, but you look at other Mars simulations, Mars 500, isolation studies, there certainly have been useful things that we have learned from that. There have been insights and very useful data that we've gained, but I don't think that any of them have gone to the level that we're going to go with this mission. And I listed 8 factors here. You've got extreme isolation with very limited access and resupply capability. The duration of the simulation, well, certainly there have been, Mars 500 was certainly longer. This is a good length of time. If you talk to the psychologists, they'll tell you that if you put a crew in isolation for a short period of time, say up to several months, they can basically tough it out. Well, you're not going to be able to do that in this mission. So you're going to see some really interesting things happen from a psychological perspective with this crew. And hopefully we make the right choices in the selection of that crew so that these are positive things and not necessarily negative things. The cold temperatures, certainly that's important. The Mars analog environment, which I already talked about. The fact that you've got the crew in what is a very realistic habitat. Now, certainly some of the fixtures and finishes might be a little rough or inaccurate, but you're in this remote Mars-like place in I think, a pretty good representation of what an initial Mars habitat would be like. So I think that certainly plays into it as well. You've got the crew up there doing realistic science. They're testing equipment. They're testing procedures, various pieces of technology that are very similar or representative of what initial human Mars explorers would have to try to use. And instead of just sitting in a lab environment, in a major city, they're actually out in this remote field environment doing hard work in a harsh environment with schedule pressure. So this is very realistic. And also I think it's important to note that this is going to be a very high visibility, high profile type of project. The public is going to have their eyes on this, especially with all the news, all the coverage in the news these days about various Mars initiatives and space initiatives. So, people are going to follow the story. They're going to want to identify with the crew. We're going to want to step up our game in terms of how we publicize and how we capitalize on this interest. So, to sum that up, I really feel that in order for us to really understand what are the challenges that will be faced by the initial Mars explorers, we need more realistic Mars simulations. And this, I think, is going to go far beyond anything that's come before. So we actually have broken this Mars Arctic 365 into 2 different phases. Phase 1 occurred this summer. It was basically a survey and refit mission, and I'm going to talk to you in detail about what happened during that. Phase 2 is going to be us going up and completing the refit and then leading into the 1-year Mars simulation. So what did we accomplish this season? Quite a few things, actually. We delivered a new generator. the generators that were up there were more intended for temporary standby use. They weren't intended to be run nonstop for a year. And so if you think about putting people into this environment that's so hard to get to and it literally is life-threatening. If you go outside in the depth of winter and you don't have the right equipment, you don't have the right clothes on, I mean, this is a lethal environment. So we have to take this very seriously. The level of equipment and infrastructure and backups that you're going to need in order to do this safely is quite different from what we've had to deal with for, say, a one-month expedition, which is the typical up there during the height of the Arctic summer. So we're bringing up we brought up one new generator. We're going to bring up another new generator next season. We delivered a new ATV. We actually had Arctic Cat provide a pretty significant discount. So we have one that we actually flew all the way onto site and made use of, and then we have another two that we purchased and got up to Resolute and we'll bring in next season. We deployed an Instaberm, which is a containment area for holding fuel drums, and we stockpiled some fuel, and we're going to have to bring a lot more fuel in to support running a generator 24/7 for 365. We also brought in some new cooking equipment, and we also brought up a metal storage shed. And this is important not only for storing equipment and materials that we're going to need for the one-year mission, but it's also important to protect our investment in these new generators. So we're going to actually put the generators inside the shed. We also had another company called Tempcoat donated this pretty amazing insulating paint. It's these little ceramic spherules in a latex matrix that we're going to apply to the underside of the hab. If any of you are familiar with the story of how the hab was initially constructed, there was a paradrop that failed, and that paradrop contained all of the floors. And so while the walls and the dome of the hab are very well insulated, they're this honeycomb fiberglass material with about an R50 insulation value, the floor is just plywood. So we really need to do a better job of insulating the hab so that we make sure we keep the crew warm. And we've got it up, it's in Resolute, and we're going to take it over to the station and apply it next season. We also assessed the ground conditions right where we were going to install this shed because we weren't sure exactly how difficult it would be to drill into the permafrost and could we put anchors in. And we were amazed, actually. It was very easy to drill into the permafrost. And if you put a metal rod down into this hole you've drilled and you just come back 30 minutes later, you know, the water has, where it was on the surface, it had become water instead of ice. It had all come in there, and it actually makes this metal rod now part of the permafrost. It's kind of like the sword in the stone. You can't pull it out. And it turns out this is how they anchor buildings routinely all over the Arctic. So we won't have any problem deploying the shed next season. We surveyed a couple of new airstrips. We wanted to make sure that we don't run into a situation where a plane's trying to come in and land and we've got a crosswind. So we wanted to have another airstrip that was perpendicular to that one so that we could make use of it in that case. We also delivered a new weather station. The weather station that is on site hasn't worked for a long time, so we brought a new one up. And we had Iridium donate a couple of satellite phones, so we made use of those up there. Of course, we did some cleanup, organization, and very importantly, we surveyed the station. No one had been there since when I was actually the last one on site in 2009. So before we started this expedition, we didn't even know, is the thing still standing? Has the floor collapsed? So we got up there and we looked at it, and everything was exactly as I had left it in 2009, so that was a very good sign. And I got to tell you, that station is very well designed and constructed. The structure itself is very, very sound, so no problems there. We did identify some stuff that we need to do on the inside, though. So we have this cabinetry in the upstairs of the hab, and because it's so well insulated and sealed, moisture tends to build up there. And so we had some mold issues, and so we're going to be replacing the cabinetry, we're going to be replacing the carpet next season, and going through all of the electrical and plumbing systems just to make sure everything's up to snuff. We don't have a fire, we don't have a flood for the crew. So that's pretty much what we accomplished this summer. Next summer, we're going to continue the refit activities. Probably it'll be about 2 to 3 weeks on station for the refit crew, and then I'm hoping there can be a little bit of overlap. We can bring in the full-time crew and have some training of them on how the systems work and how to maintain them before the refit crew gets out of there. Let's see. I mentioned a lot of this. We're going to be delivering more ATVs, some snowmobiles, because when there's 2 feet of snow on the ground, that's how you're not going to be using the ATVs. Get the shed up, install the generator, install a second generator. And then one of the things also about these generators is instead of having the radiator for it incorporated as part of the generator, we actually have remote radiators. So we'll actually be able to put one of these right outside the shed, and then the other one we're going to install inside the hab. And so we can take all of that waste heat from the generator, and instead of dumping it into the environment and wasting it, we're going to dump that directly into the hab to heat the hab in the wintertime. So that'll be really good. Let's see, bring in more fuel, bring in food. Obviously, there's going to be a lot of food they're going to burn through over the course of a 1-year expedition. And I've got some pictures here. So this was the ATV that we picked up in Yellowknife and brought on site. Here we've got some buckets of the temp coat insulation, and then there's the shed being delivered to our staging location in Yellowknife. So I've got some pictures. I'll kind of pictorially walk you through this year's expedition. One of the things we were really fortunate to have this season was we had a couple of private pilots. They own their own bush planes, their own Kodiak, Quest Kodiak aircraft that you see here, the yellow one and the blue one. And these are capable of flying us all the way up to the Arctic and actually landing on the dirt airstrip on Devon. So they were gracious enough to provide use of their planes, their piloting skills, and all of the fuel to get us and our gear up there and back. So that was just phenomenal. Because usually what we have to do is rely on Twin Otters that we have to charter at great expense, and we didn't have to do that this season. We also, I want to make sure that I point out and thank Barry Stott. Barry is there in the audience. Barry made a very generous cash contribution to this mission, in addition to being instrumental in the planning of it and in the actual execution. So the plane that you see in the background between the 2 Kodiaks there is Barry's 421. So he actually flew some of the gear and the crew up the Yellowknife, and it was very important that he was on the ground there in Yellowknife and could help manage logistics for us. So thank you very much, Barry, for making this possible. So we all met in Driggs, Idaho, which is where the 2 Kodiaks were based, loaded up, and started flying north. We started by flying over the Grand Tetons, which was just spectacular. So I was actually in the back of the yellow Kodiak here, taking a picture out the window, and you can see the blue Kodiak in the distance there with the Tetons in the background. Got some good shots. We flew in formation the whole way up. And the further north you go, the more bleak the landscape gets. So, this was, I think, somewhere just north of Yellowknife, and you could see that we've gotten well past the point where there's forests and trees, so you just kind of have grasslands. Of course, then if you keep going further north, it starts to look like this. So this was actually a picture over Devon Island when we were going to put into the station. So we landed on Devon, and we found that it was a much wetter, colder place than I had experienced back in 2009. In 2009, apparently, we had a pretty dry year, a warm year, so things had all dried out. All the snow had melted pretty much before we got there, and there wasn't much mud to speak of. It was pretty dusty. That was not the case this time. So I don't know if this has something to do with climate change or what, but we got there, and this is the creek that was flowing very high, and this big snow banks. This was at least a foot thick snow. So there was some shoveling involved in order to get everything over to the hab. But we did get up to the hab. We actually went in with a spearhead group, myself, Justin Sumter, and Adam Nair. So this is us in front of the station there, I think the first or second day. And as I said, the hab was in very good condition. It was pretty much as I had left it in '09, with one exception. So in '09, we had put in place the secondary containment area, which was basically rubber stretched over boards that we put our fuel drums on. And if the fuel drums leaked, then it would catch the fuel and keep it from going into the environment. Well, this is what's left of part of that secondary containment area. So this is evidence of a polar bear finding this kind of interesting and digging into it. And quite frankly, when I was on site and I saw this, it was terrifying. I actually brought back a souvenir. So later we were walking down the ridge and I found the missing piece of that Instaberm. And so if you want to come up later and take a look at this, you can see where the bear put his claws into it, where he chewed on it and actually ripped it off. So we're going to be auctioning this off a little bit later. Nice little souvenir. So I mentioned all this thick snow. Yes, unfortunately, I did get our new generator stuck in a snowbank. But not to worry, we had a resourceful crew on site, and we were able to load it up and get it over to the hab. We also, I mentioned we deployed the Instaberm, so this is what the Instaberm looks like with a couple fuel drums in it. So this will actually hold 30 drums. We're going to need somewhere on the order of 100 drums to run one of the new generators continuously for a year. So we'll have to kind of evaluate, depending upon what kind of aircraft support we have next summer, whether we bring in more Instaberms and more fuel all at once, or if we do it kind of over time as the mission progresses. Of course, we had to do some of the things that are FMARS traditions. So the crew always signs their name on the whiteboard as greetings for the next crew. And then in each stateroom, there's a place where each of the crew members that stayed in that stateroom sign. So obviously I was there in '09, so I got to sign this one twice. And then you can't leave FMARS without having some cheese whiz. And yes, the crew did watch Mars Attacks. So we were working pretty hard up there because we had a lot of tasks that we were trying to accomplish in a very short amount of time. But I did feel as crew commander, these guys deserve a little R&R. We got to go out and let them see a little bit of the island. So we took a hike over to Cornell Lake, which is a couple miles from the hab. It's within walking distance. Of course, we had to carry our guns in case of an encounter with a polar bear. But I mentioned that Devon was a wet, muddy place. Well, I think you can see in this photo, this was actually before we got the mud guards up from Yellowknife. We got the ATV on site, but not the mud guards. So it was pretty dirty. And Justin kind of found out the hard way just how muddy a place it was. He had an encounter with the infamous Devon Island quick mud. So he's a much taller guy than he looks in this picture. It's because from the knee down, he's in the mud. Basically what happens is the surface layer dries out, and it looks like good, stable ground to walk on. You walk on it, and you pass right through that layer, and there's a thick layer of mud until you get to the permafrost layer. So he was in no danger of, sinking up above his head and drowning, but he was stuck, really stuck. So I had to go over and pull him out, and we did save him. He wasn't too happy about the experience. And we also did a very short EVA the last night before we pulled out. So here's Adam getting all dressed up in the spacesuit and heading out and just getting a feel for how that was. Just a pedestrian EVA down the ridge and back. And at one point there, we had the pilots flying back and forth to Yellowknife, bringing up more supplies and equipment, and the other crew members that couldn't come up on the initial trip. So we've got Justin, we've got Rich Spencer, that's Rich Sugden. There I am, Adam. That's Garrett Edquist, who's going to hopefully be putting together a documentary video about FMARS. And then Rich Spencer, one of the other pilots, and Alex Kumar. And this was the last photo that we took from the air of the HAB as we were flying out, showing the HAB and the infrastructure, waiting for us to come back and finish the job that we started, finish it next year. So in summary, get involved. Please spread the word about what we're trying to do here. Contribute generously and help us make this mission possible. Thank you. Let's take a couple questions. Anybody? Yes. I'd have to go look up the numbers. It gets pretty strong up there. We did take that into account when we selected the steel structure, but I don't remember the number off the top of my head.
Does it ever get so cold that you have problems with the viscosity or solidifying of your diesel fuel in the winter?
Not the diesel fuel, or even I think the gas and the propane would be a problem. One of the reasons that we replaced the stove in the kitchen and the HAB was because it ran off of propane. And the propane, number one, it wouldn't be any good in the cold temperatures, it kind of gels. And number two, we had a real problem with humidity buildup. And if you're basically having combustion in the upper story of the HAB, it's sealed so tightly. In '09, we had problems with the water literally dripping down onto our heads from the ceiling from the condensation. So we've gone completely electric in the HAB at this point. There is no more propane. Yes?
What's the distance that, the furthest distance that operations would take place from the HAB? What's safe for the crew to go out to if any of the science missions take place? Will they be spending any overnights outside of the HAB for any of the science?
I don't know if they're going to spend, I don't think they're going to spend any overnights outside. Typically what you want to do is not travel so far in the ATVs that if they break down you couldn't walk back in a reasonable amount of time. I know that, I think it was the '07 crew actually staged fuel a distance out, so they kind of broke that requirement. They went much further than they could walk back because they wanted to get to the shore and actually see the shore. So we really haven't set all of the operational parameters yet for the one-year expedition. We're going to have to think about that, though, because again, if you get stranded out there and you're a good distance from the HAB and it's 40 degrees below, this could be problematic.
Sure.
Take a couple more. Yeah.
Is there a plan on incorporating some kind of 3D printing with the advent of 3D printing strides we've made in making that fluid affordable? It's probably realistic that in the future when we have an actual Mars mission, that'll be an integral part of the space app on Mars. Is there any plans of doing something like that so we can make repair parts and stuff from programs, flash drives, if you break something?
Well, certainly, I think that's a capability that a real Mars mission would want to have. You can even have theoretically a part break that you can predict would break. People on the ground could email you the file and you can print out the part. I think it would be great if you have a 3D printer at Mars. And I know one of the things that we're going to do as we gear up for this is to reach out to entities and individuals all over the world that might want to work with us on various aspects of the science program and research that we'll be doing this mission. And it would be great if we could get somebody to work with us on a 3D printer. That'd be cool. Last question. Go ahead.
Good job, Joe.
Thank you.
Presentation. My question is, with regards to food, diet, and nutrition, are you going to follow or take some of the findings from the recent high seas exploration? Why?
Well, I know we're working with Jean Hunter, who is helping us very much with the food and the menu and all of that. She helped us select what food to take up there to pre-position this summer. And I'm sure we're going to be bringing a lot more food in, so I'm pretty sure she's going to still be involved in that. And I think she also had involvement in the High Seas project, so I'm sure that there will be some cross-pollination and lessons learned applied there.
final award of the evening is going to go to Dr. Stephen Squyres, the principal investigator of the Mars Exploration Rover mission. Now, people have seen a lot about this mission, and you're going to hear a lot more about it tonight from Steve. But this was an amazing accomplishment, not just, the word justice is not quite the right word, not only in the actual doing of the mission and its scientific findings and the brilliant engineering that allowed it to succeed, but in making it happen at all. Okay. Okay. I had no role in this mission. Okay, but I did go to maybe 5 or 6 of the 2 million meetings that Steve had to go to to try to make this mission happen and keep making it happen in the face of, various things happened. The 99 missions failed, this, that, decisions change, you think you have this thing in the bag, and then the bag is thrown away, and, and so forth. And I mean, I can just tell you, in terms of this environment, that this guy made this rover mission a crusade for over a decade before it actually came to be. And let me give you an idea what things are like in the early 90s, going to meetings of the Mars Exploration Working Group, or whatever the hell it was called. And there's people trying to convince these scientists of the merit of having the rover on the Pathfinder mission. Okay, well, the scientists didn't like a rover. They thought rovers were bullshit. Rover, that's just public relations of rover. What do you want to put a rover on Mars for? That's ridiculous. Okay, and the second most hated instrument, by the way, on the lander, anyone after the rover, anyone can guess what the second most hated instrument by the scientists was? The camera, precisely. Okay, because that's just public relations. Photographs, I mean, that's just for the public. Real science is numbers and, blah, blah. And they didn't like the camera either. That's just bullshit. And and of course, I mean, look, frankly, I would also go to some of their meetings where they would expound their various theories about whether Mars was warm or wet in the past or not. And everybody is arguing from imagery. Okay, that's what everyone's arguing for. Because after all, as human beings, our primary sense is vision, and that's how we comprehend the world. And, but precisely because the public could also understand imagery, they wanted to restrict it to, seismometers and proton spectrometers and all kinds of crap, and none of which worked. But anyway, he went to all these meetings again and again, and made this thing happen. Got it through this incredible bureaucratic process, and then led the technical effort to make it succeed, and then to carry it out. So this is an incredible achievement. It's almost beyond comprehension, okay? And so we have, a trophy for Steve.
Oh my goodness.
Okay. Okay. So, the symbolism here may be somewhat obscure. Okay, but you earned it. So come on up, Steve.
Oh, that's fantastic. It's heavy. It's fantastic.
I will read the plaque. It says, okay. Okay. Right. The Mars Pioneer Award, presented to Stephen Squyres by the chapters and members of the Mars Society at the 16th International Mars Society Convention held in Boulder, Colorado, USA, August 15 through 18, 2013, for outstanding achievement in advancing the exploration of Mars.
Thank you. Well, thank you, Robert. That award is given very generously and received very gratefully. Individual honors in team sports are always kind of a strange thing, and there is nothing I know of that is more of a team sport than Mars exploration. And so I accept this, but on behalf of the whole membership of the Mars Exploration Rover team, all 4,000 of us, thank you very much. Okay, so as I'm very fond of saying, today is day 3,400 of our 90-day mission to Mars. And opportunity is still going strong. This is a front HazCam picture that came down a few hours ago. It shows the front view out of the front end of the rover as it stands right now. And it would be easy to think all these years later that somehow the process of getting a rover to Mars was sensible, was logical. It was not. And Robert sort of gave you a sense of it. Believe it or not, there was a time when it was incredibly hard to convince people that sending a rover to Mars was a good idea. And part of the problem, I think, arose from this magnificent success, the Viking lander mission. Fantastic success, great mission, but look at Mars. To many people, that was Mars. Absolutely flat, with identical looking boulders stretching to the horizon in all directions. Why do you need a rover when all the rocks look alike? This was a battle that I fought for years and years and years. I spent 10 years, from 1987 to 1997, writing a succession of proposals to NASA to try to do something like a rover mission to Mars. And each one of them was shot down in turn, like so many clay pigeons. And finally, on the fourth try, we were selected. This was what our rover was going to look like at the time that we were selected, and it was actually part of a Mars sample return mission. This was a Mars sample return mission. We were going to launch in 2003. The samples were going to be back by now, 2013. We were going to launch the first rover in 2003, the second rover in 2005. The mission to return the samples was going to be launched in 2008, and they would be back on Earth by now. Here's our little rover hiding behind a rock so it doesn't get toasted while the Mars ascent vehicle takes off and sends the rocks up to orbit. But then some bad things started to happen. The first bad thing that started to happen was NASA realized that we didn't have enough money to do this. And so the program sort of began to disintegrate. And at one point, they took our payload, which had been designed to go on a rover, and they put it on this lander with this tiny little rover that would run around, but it didn't really go very far. This is like a geologist with his boots nailed to the ground. Okay, that was what this mission was going to be. Then things got worse. There were the missions, the two missions that were launched in '98, Climate Orbiter, Polar Lander, Mars Lander, Silent After Descent, NASA Chief Future Mars Missions in Doubt. They wiped the slate clean. The entire Mars program was blown away. I had a completely calibrated, tested payload 6 weeks away from going to the loading dock at Lockheed Martin in Denver, and the mission was canceled. So we regrouped, and we came up with this cockamamie scheme of trying to put a rover inside the Pathfinder lander and land it with the Pathfinder airbags. This is the drawing of the MER rover as it was conceived at the time. This was with the press release that came out when they announced the selection of the mission. Notice that there's only one rover. Two came along later. Notice also there is no instrument arm. The artist kind of forgot that. But this is what it looked like at that point. Once all was said and done, it looked more like this. And this is the rover that we all know and love with the 6 wheels and all the instruments on the payload and so forth. Now, the vehicle that we came up with to deliver this rover to Mars was based very much on the Mars Pathfinder vehicle. The rover, in order to fit into that vehicle, had to fold up in this horrifyingly intricate fashion to fit inside the lander. The lander has these 3 petals on the side. We call them petals because they're like the petals of a flower. They fold up around the rover, encasing it, protecting it. So this is what the lander looks like when it's all folded up. It looks very much like the Mars Pathfinder lander. It's then, in turn, encased in another shell. This thing's built like one of those Russian doll sets, you know, where there's a doll inside a doll. It's like that. And this is in another shell, which is composed of the heat shield and the back shell. And then this kind of frisbee-looking deal on the back end, that we call the cruise stage. And it has propulsion and electrical power, the stuff you need to get you to Mars. So here's what it looks like, all buttoned up. This is the Spirit spacecraft at a JPL on a thermal vacuum test. Now, to land on Mars, you got to deal with the fact that you arrived there going really fast. We hit the top of the Martian atmosphere going Mach 27. 27 times the speed of sound. The heat shield bleeds off that kinetic energy, and then once you slow down to a nice leisurely Mach 2, you throw out a supersonic parachute. We learned the hard way that supersonic parachutes are very difficult things to design and build. The lander descends on the long cord, and this is what the vehicle looks like. It's still screaming down towards the Martian surface at about 300 kilometers an hour. You do not drift down lazily on a parachute on Mars because the atmosphere is so thin. We had a horrible time with the parachutes. I remember this very well. This was the first test that we did of the parachute design that we thought was going to land us on Mars. We did this test at a National Guard gunnery range outside of Boise, Idaho. It's the kind of place where you can drop big, heavy things from the sky and they won't kill anybody. And we dropped our test article from a helicopter of 4,000 feet, deployed the parachute, it blossomed, made this perfect orange and white bowl, and it just exploded. It just ripped into ribbons, and parachute after parachute failed. What had happened was the vehicle, by the time we got to these tests, our estimate of its mass had become so high, it was so heavy, that the parachute could not land it. So we had to embark on a crash program of parachute redesign, designing 3 parachute designs in parallel, praying that one of them would work. We did these tests at NASA Ames Research Center in a wind tunnel, and we finally did get one of them to work. This is the actual parachute design that landed us on Mars. We finally got this design to work 8 months before we had to be on top of the rockets in Florida. It was horrifying. We land using airbags, okay, just like the airbags in your car, except a lot what? That's an airbag engineer at JPL being consumed by his work. They inflate explosively around the vehicle, and they drop to the surface, and they bounce, and they bounce, and they bounce, and they roll, and they roll. And they can bounce and roll as much as a kilometer before they come to rest. This is from our first airbag test, and you've had days like this, right? You can sort of tell from the looks on their faces it's not going real well. We tested these bags, and when we tested them, they just burst. They just exploded. And again, what had happened was the vehicle had become too heavy. So we had to add more layers to the bags to strengthen them, which of course made them heavier, which made the parachute problem worse, and so forth and so on. We did get it to work. This is a picture from one of our successful tests, and of course the ultimate test, these are actually airbag bounce marks on the surface of Mars. It was nice to see. You can almost see the stitching in the seams. So once this thing lands, the lander opens up, flips itself upright, and then this rover doesn't look anything like a rover yet. It's still stowed inside, and it's got to now do origami in reverse, unfolding itself and turning itself into a proper rover. And there's so many gears and motors and springs and hinges and latches that have to work just right during this process. I mean, what you see right now, these are the solar rays coming out. These are the life-giving solar arrays which, if they do not deploy the first day on Mars, we don't survive the first night on Mars. The camera mast comes up, the antenna goes out, and by the time it gets to this configuration, the vehicle is safe. Everything you just saw happens in the first hour or two after landing. So now we got sunlight, we can take pictures. We can't go anywhere yet, though, because the whole suspension system is still stowed underneath the vehicle. There's more to come, and it's worse. Watch this. There's this jack, like the jack in a car, that lifts this thing up, and then watch what the front wheels do. Ugh. I mean, all these years later, I still get the heebie-jeebies watching that. If those latches don't latch, you're done. Everybody in this room has seen the famous Curiosity, 6 Minutes of Terror, that cockamamie, crazy, terrifying-looking sky crane system. Part of the reason that was designed was so we wouldn't have to do that again. Now, we thought once we got to this point, with the rover standing up on the lander deck, we were good to go. We could just go monster trucking down onto the Mars surface and everything would be good. Then we did some tests. Yeah, this was a bad day. You drive one of these things off a lander, the rover can flip itself upside down. Another problem we had to solve. What we came up with, you saw in the video, we came up with these ramps. They're made out of fabric and they stow between the pedals. And then when the pedals open up, the rover is able to drive down the ramps that are formed by the fabric. It's made of the same fabric that the airbags are made of. Very tough stuff. Once you get on the Martian surface, you got to deal with the fact that it ain't exactly paved. And so our mechanical engineers came up with this rocker bogie suspension system that was able to allow the six-wheel design to conform to the topography of the Martian surface. This shows how it works. Just watch the wheels. It's pretty slick. I mean, we find a corrugated metal roof on Mars, we're good. But it's a remarkable system, and it works. The process, I wish I could convey to you my memories of this and what it felt like to see things that had once been sketches on the whiteboard in my office begin to become engineering reality on the way to Mars before our eyes. That process of taking this concept and turning it into real flight hardware was a memory I will treasure for the rest of my life. We built the rovers, we tested them, then we had to ship them to the Cape. We put them all in a Atlas Van Lines truck. Rob Manning blew a stirring bugle call on his trumpet, and we drove it off to Florida. And then we unpacked. When we unpacked at the Cape, we had a lot of stuff, a lot of hardware. So this is the room at the Cape where we put everything together, and you can see bits and pieces of rover and flight system hardware all over the room. Now we had to put it together, but this time we're putting it together for the last time. And every connector that gets mated, every fastener that gets tightened down, if you don't do it right, that's it. So very, very, very cautious, very painstaking work down at the Cape. This is making sure the rover will fit inside the lander. I thought I had an exciting job. These are the guys who have to mount the solid rocket motors onto the vehicle. They have a really exciting job. This has always been one of my favorite pictures from the Cape. This is Spirit in the foreground. That's me. Opportunity in the background. This was Media Day. We brought all the world's media down, got them all in the suits, and we brought them in here, and we set this thing up. We were going to command the rover to drive. The story that's not often told about this picture is that a minute or so after this picture was taken, the rover drove. This is a rover that's ready to go to Mars. We commanded the rover to drive, and a washer fell from its belly onto that blue mat. You have never seen more freaked out engineers in your life. I still don't know where that washer came from. We just picked it up and put it away. True story. I don't think anybody in the media caught it. It was an ugly moment. Anyway, we buttoned it all up. This was the night, 2 o'clock in the morning. I remember driving behind this truck in my rented Chevy 3 miles an hour, all the way out to the launch pad at dawn, watching them lift the thing up to the top. There are a lot of downsides to being the principal investigator on a mission like this. There's a lot of reviews, a lot of meetings you got to go to. But there are a few decisions as PI that you get to make that are kind of nice. One of the instruments on our payload required a dry nitrogen purge. That was dry nitrogen that was flowing into the instrument to keep it dry until a matter of hours before launch when the purge had to be disconnected. It was important for somebody from the science team to be there and make sure that was done properly, and I decided that was the principal investigator's job. So the night before we launched, I got to actually go up to the top of the rocket and watch them disconnect the purge. They did it just right. I never thought, it was 16 years between when I first started working on this and when we actually launched the things. It was 16 years just to get these things to the launch pad. But we launched them, and we got them on their way to Mars. Now, this shows the trajectory that we followed to Mars. It was about 7 months. People who didn't know anything about spaceflight would say to me as the rovers were on their way, well, now you get 7 months off before you have to start working hard again. Okay, another really ugly true story. When we launched Spirit and Opportunity, excuse me, can somebody get me is there some water? When we launched Spirit and Opportunity, the software, the flight software for launch, cruise, and landing was on board the vehicle, fully tested, ready to go. The software for driving wasn't written yet. True story. We wrote it, thank you. We wrote that software in 5 months. We tested it, and then we launched it at the speed of light, and it caught up with the spacecraft 2 months before the spacecraft got to Mars. We had to earn our Martian driver's licenses, and we spent that whole period doing operations readiness tests, figuring out how to operate the rovers, figuring out how to operate the vehicles. Every operations readiness test was a complete, colossal failure. Remember, one of the things that we had to do in our tests was acquire, you probably remember seeing them when we landed, these big panoramas. We called it our mission success panorama. One of our operations readiness tests, 3/4 of that panorama just disappeared into our computers. We never found it. Imagine what that press conference would have been like. Once we got to Mars, it all worked. Landing night was pretty tense. When it does work, it feels really, really good. We got to feel really, really good for about 18 days. This is day 12 of the mission. One of my favorite pictures of the mission. This is the picture that proved that we had 6 wheels in the dirt on Mars. Eight days later, things completely went to pieces. Sol 18 with Spirit, we lost control of the vehicle. It looked like the mission was over. It was horrible. It was a software problem. We finally got it back. This is another one of my real favorite pictures from the mission. This is the first picture that came down after we recovered the spacecraft, and we actually had a functioning rover on Mars. 3 days later, Opportunity landed. So it was a pretty busy time. Driving on Mars, excuse me. Driving on Mars is a difficult thing. What I wish I had, of course, is a joystick. You know, what I want to do is be able to drive it around rocks, but with the one-way light time delay, you can't do it. And so we've had to endow the vehicles instead with vision and intelligence and the ability to make their own decisions about what's safe and what's not. And we can program different levels of courage or cowardice into the rovers depending on how tough we think the terrain is. It takes these pictures, then it generates a terrain model and figures out what to do. This is actually some data early in the mission. This is Spirit. This first part of the drive, we told the rover what to do, but from here on, the rover's making its own decisions. So it's driving along, and right here, finds a scary pile of rocks, doesn't know what to do, thinks about it, says, okay, I can do this, I can do it backwards. It does make that beep, beep, beep sound as it's backing up. Another pile of rocks here, thinking about it, okay, and they told me to stop right here. All done. They're pretty smart little vehicles. Now, while the vehicles are pretty smart, sometimes the team on the ground is a little bit less so. And about 600 days into Opportunity's mission, we came in one morning, and this is what we found. We were using a driving technique at that time, which I will describe charitably as bombing along at top speed with our eyes closed. We were driving over sand dunes that we thought were safe. But what happened was, at one point, the wheels broke through a crust, and we did 50 meters of wheel turns, thinking we were driving across the surface, when in fact we were just digging deeper and deeper and deeper into the soil. And we come in, and all 6 wheels are buried over the hubcaps. Now, when we built the rovers, we built 4. 2 went to Mars, 2 were on Earth, and we used those to simulate predicaments that we've gotten ourselves into, and then try to figure out how to get out of that predicament. To simulate this particular predicament, we needed a very large quantity of fake Martian soil. Should you ever be called upon to produce fake Martian soil, this is the recipe you should use. Equal parts play sand, the stuff that's used in kids' sandboxes, clay, and diatomaceous earth, the stuff that's used in swimming pool filters. Okay, and once we figured out this recipe, a bunch of engineers in pickup trucks fanned out across the LA basin and bought up literally tons of these 3 ingredients. People were getting algae in their swimming pools all summer long because of us. And we came back and we set this up, and we spent 6 weeks trying to rehearse, trying to figure out the optimal way to extract a robot from a sand dune on another planet. You can do lots of things. You can steer the wheels back and forth to open up the holes. You can rock the vehicle. You can run the wheels at different velocities. We tried all of those things and many more. We ultimately found the optimal technique, which it turns out was to put it in reverse and gun it. There's no place you go to look this stuff up. So here we are, gunning it on Mars. We had to do 192 meters worth of wheel turns to go 1 meter on Mars. But after 6 weeks, we finally popped out of this feature, which we came to call Purgatory Dune. And we've been treating those dunes with much greater respect ever since. Our adventure has continued. I'm not going to tell you the whole story of all our discoveries. You heard a talk from Jim Bell about both curiosity and opportunity earlier today. But Spirit lasted 6 years. Opportunity, 38 kilometers, 9.5 years of operation, Sol 3400. This was a picture a few hours ago. We're still going. I thought I would say a word or two about this. One thing that many people have asked us over time has been, what's the secret? What was your secret? What was the secret to success on this mission? There were many, but if I had to point to one thing, if there was simply one thing that was the key to success above all else, and this is going to sound so simple-minded, but it's that we knew exactly what it was we were trying to do. We knew precisely what we were trying to do. Now that sounds idiotically simple, but I have seen more enterprises at all levels of complexity fail because everybody involved did not have a common vision of what it was they were trying to achieve. That document, I don't expect you to read it, but it's a half a piece of paper. That is the entire mission success statement for an $800 million Mars mission. That's it. You could memorize it. You sleep with it under your pillow. And the beauty of this incredibly crisp, clear description of mission success was that it lent a crystalline clarity to every decision we ever made. Do we fly this piece of hardware? Do we not? Do we hire this person? Do we not? Do we do this test? Do we not do this test? If it's necessary for mission success, you have to do it. That's it. If it's not, it's expendable. Beautifully simple. There were many times that all of us doubted whether or not we were going to succeed. But there was never a single moment on our project when any of us doubted for a second what it was precisely we were setting out to do. That was incredibly important. Let me talk a little bit about the future of Mars exploration now. This is the plan as it exists right now. This is sort of by year. Spirit and Opportunity, that mission's still going. Mars Express, Odyssey, MRO, Phoenix. Here's Curiosity doing incredible stuff. Maven launching very soon. In 2016, ESA's Orbiter, the InSight lander doing geophysics. 2018, the very ambitious ESA ExoMars rover. And then 2020, the 2020 rover. And that's the beginning of Mars sample return. This has been the holy grail of Mars science for a very long time. And that will be followed. This is where it gets a little hazy. You just get a sort of gray arrow that says future planning on the NASA chart. But the objective will then be to get the samples that were collected by this rover and bring them back to Earth. This is what the rover looks like, and the central focus for this rover, you notice it looks like Curiosity, but it's got a very different job. Its job is to collect and cache in a little precious canister, little spacecraft ultimately the size of a coconut, a suite of samples that will be brought back to Earth. So I thought it might be interesting to just spend a few moments talking about some of the lessons that we've learned from 9.5 years of operating rovers on Mars as they might be applied to this future problem of collecting samples. First of all, I'm really glad there's going to be a rover. Mobility is incredibly important. A huge fraction of where we explored at the opportunity site looked like this: sand. And if we had landed here with no mobility, all we would have seen the entire mission would have been sand and a bunch of little freaky round hematite balls, and that would have been it. Try to figure that one out. That's not a real valuable sample set to bring back to Earth. So mobility is really important. Being able to land accurately is obviously important, and that's the trick that we're playing on Curiosity. Curiosity was able to land very accurately, and so the Curiosity landing site is snugged in real close to this big, dangerous Mount Sharp. We can't land on Mount Sharp, but we can land next to it and then drive up to it. But still, mobility, even if you can land accurately, mobility is still incredibly important because you want to get diversity. This is a complicated geochemical plot, but it makes a simple point, and that is that we have found a whole bunch of different kinds of rocks with our rovers. And the reason is because we can drive so far. All those rock types that I showed you in that last plot were collected, were examined at various spots during this ascent of Husband Hill. We were not able to do that except that we had our mobility. So mobility is incredibly important. Longevity is also incredibly important. Spirit's biggest discovery, or one of the biggest discoveries, the silica at Silica Valley, was made 1,200 sols into its 90-sol mission. So I'm very, very glad that there's that big lump of plutonium on the back of this 2020 rover that's going to give it a long lifetime. Another important point, and this is really significant for thinking where we're going to land these things, it is incredibly valuable to have high-resolution images for planning traverses. In fact, I claim that it's really necessary to do it right. We used it at Victoria Crater. We used it at Home Plate. You can see the tracks made by the rover. And my point here is that we currently have only a tiny fraction of the surface of Mars covered with these incredibly high-resolution images. And yet it's necessary to have those images to operate a sample collection rover well. So unless another instrument like the HiRISE camera, which is flying right now on MRO, is going to fly in the future, that means that wherever we send this rover in 2020, it's got to be somewhere in that tiny percentage of Mars that we've got good images for. That's going to really constrain the problem. Final point, there's a lot of dangerous terrain on Mars. And remember, the way this mission works is this rover has to cache the samples, it's got to collect them, it's got to cache the samples, and then it's got to put that cache someplace where another rover can come and fetch it. You got to land close to that spot. Now, some of the best places to do geology on Mars have very, very steep, dangerous, rugged terrain, and it's going to be tempting as hell to drive down into these places to get those good rocks, but if the rover can't get back out, you may never see those samples back on Earth. And so there's going to be this tension between trying to go to places that are dangerous enough to have good rocks, but still get out again. So we got a nice safe landing zone for the vehicle that's going to come next. It's going to land alongside this thing, pick it up, and shoot those rocks back to Earth. I want to conclude tonight by talking about the more distant future and human spaceflight. NASA is today beginning to develop some of the infrastructure necessary to send humans once again beyond low Earth orbit. There's the Space Launch System, SLS, initial operating capability about 70 metric tons, eventually 130-ish. This is the Orion spacecraft, can support a crew of 4 for about 21 days. These are building blocks. They're part of what you need to do the job, but they're only part, and there's a bunch of stuff missing. And there's no plan for it, there's no money for it, and NASA is unfortunately being distracted by pressures that are being imposed on it externally by the Congress, by the White House, to do a whole bunch of different things, many of which don't have anything to do with deep space exploration. Now, one of my occupational hazards is that if from time to time I'm called upon to testify before Congress about the future of NASA. I've testified several times this year. This was a hearing very recently where the witnesses were myself and then Tom Young, one of the real greats in the aerospace business and a real contributor to the history of Mars exploration. And this is what I had to say. 3 themes run through my testimony. Number 1, NASA needs a clear and compelling long-term goal. That goal should be to send human explorers to Mars, period. NASA's being asked to do too much with too little. There are too many distractions from that goal. And the result is wasted effort and delay. And this is kind of Washington, D.C. speak, but it's an important point. Our nation's civil space program will be best served by having high-level policies set by the administration and Congress and implementation details recommended by NASA scientists, engineers, and managers. Back in the early 60s, President Kennedy said, we're going to go to the moon, but Congress did not then dictate via legislation the performance capabilities of the Saturn V or exactly what sequence of missions would fly on Mercury and Gemini. They set the goal and left it to capable engineers to figure out the roadmap to achieve that. And so that is what I am trying to encourage to happen. When I testify in my role as NASA Advisory Council Chair, etc., is to try to get Congress, OMB, to kind of back off, set the high-level goals, and then let NASA actually do the job. So to conclude, Mars is a dream for all of us in this room, but we ain't going to get there by dreaming. The only way you get there is by putting your head down, and you just push, and you push, and you push, and you never, ever, ever give up. And that's the only way it's going to happen. That's the way this stuff has always happened. There are models that we can look to in history for things that are sort of like Mars exploration. One of my favorites is the history of exploration in Antarctica. And at the beginning, it was primitive. Primitive technology, first stumbling steps. You know, you try, sometimes it works, sometimes it doesn't. The technology is not the best, but it's what you've got. And you go there and you sometimes succeed, you sometimes fail, sometimes your spacecraft crashes, sometimes your teams die. But you learn. What then happens is ultimately the enabling technology is there. In the case of this, the permanent research base that exists South Pole Station. You put the people in place, you get the job done, and you establish a permanent human presence in a place where humans have never been. We've done it in Antarctica, we're going to do it at Mars. Thank you very much. Thanks very much. Do you want me to do a few questions? Yeah, sure. Bring it on. Right here. What was the biggest surprise when we actually got there? You know, I'm tempted to say that it worked. With all those exploding parachutes and ripped airbags and so forth, I didn't even think we were going to get to Florida, let alone get to Mars. I think the biggest surprise was just how tremendously compelling the evidence for watery activity was right from the start at the opportunity site. The first 60 days at the Opportunity site, we made, 90% of the scientific discoveries that we made in the first 7 years of that mission. Spirit had to climb a mountain and descend on that mountain, break its wheel, and all sorts of stuff to, over 1,200, 1,500 sols to catch up with what Opportunity achieved in the first 2 months. So yeah, I would have to say just the incredible pace of discovery in that first 6 or 8 weeks with Opportunity was, to me, the biggest surprise. I didn't think it was going to be that compelling that early. Yeah? How is Opportunity's health? For a 9.5-year-old rover, damn good. Let's see. We've got some dust on the solar arrays right now. We're getting by on about 380, 390 watt hours per sol these days, which is low but workable. It's, winter is coming on. Let's see. All 6 wheels are good. They're doing fine. One of the steering actuators, the right front steering actuator, doesn't turn anymore, so that's a little bit of an issue when we're trying to turn, but not much. The biggest issue that we have is on the rover, on the vehicle itself, is that the shoulder joint on the arm that's supposed to move it this way doesn't work anymore. So when we want to move it that way, we got to move the whole vehicle. Okay. Of the scientific payload, we got 6 instruments. 4 of them are fine, doing just great. The infrared spectrometer, unfortunately, we voided the warranty on that thing when we had a problem with the thermal system on the vehicle. We had to turn off the nighttime survival heaters for that instrument, and we eventually broke it because it just got too cold. And then the Mossbauer spectrometer, great instrument, depends on a radiation source of cobalt-57. Cobalt-57 has a half-life of 271 days. And when you're planning a 90-day mission, that seems like a really long time. We've been through 12 half-lives now, so that instrument doesn't work anymore. But the vehicle is really doing great. Right there. The Martian hemispheric dichotomy, why does that exist? The leading idea, I believe, for that observation these days is that early in its history, Mars suffered a very large impact that just blew a lot of the crustal material off the northern hemisphere and so thinned the northern crust and thickened the southern crust. And then when it isostatically adjusts, the north sits lower than the south. Yeah. How much water is there on Mars? That's a really, really good question. I mean, the units that one could conveniently use to describe the amount of water on Mars is equivalent liquid water depth if you had an ocean and you spread it uniformly over the whole planet. Reasonable numbers, I'm waving my hands here. Reasonable numbers are maybe 100 meters, okay? So I'm talking about all the ice that's in the polar caps, all the ice that's beneath the ground, the total endowment of water on Mars. There is reason to believe, based on isotopic ratios and so forth, a reasonable guess might be, if you could put it all at the surface in a single layer, 100 meters. But that's a wild guess. Yeah?
Are there any low-flying missions that will be considered a plan for the future? Maybe, like airplanes and other things?
Airplanes, yeah, there have been a bunch of missions. I mean, the ratio of good ideas for Mars missions to Mars missions that actually fly is very, very high. And there are missions there are airplane missions. There was the Ares mission. Yeah, I was a member of the Ares mission team. My wife loved that one. It flies for 4 hours and then it crashes. It's done. She thought that was great. There are a lot of concepts out there. They're competing with one another. The only ones that are selected are the ones that I showed you on that chart. And a mission ain't a mission until somebody's willing to pay the hundreds of millions of dollars to make it happen. There are ideas galore. Ideas are cheap. Yeah? There certainly were a lot of lessons learned transferred across. I mean, if you look at the design of that vehicle, it has a number of elements in common with some of the things that we've done. Some that are quite different as well. Some that are very innovative. So, I would say that they looked at what we did. They learned from what we did, and then they applied some very creative ideas of their own. So it's a mix. Yeah.
If you were to visit Mars, where would you visit?
Me personally?
Yeah, well, if you were going to retire.
Oh boy, if I could go to Mars. Can I bring stuff back with me or not?
One-way trip.
Okay, so one-way trip. If it was a one-way trip, I'm not going. Okay, but if I could bring stuff back with me, then of course I'd be thinking, well, this is Mars sample return, and I've got to pick my choice carefully for scientific purposes. But I think the essence of your question was, where would I most like to go on Mars? If you could just set me down, give me 5 minutes to poke around a little bit, and then come home, I think I'd pick Eagle Crater, the place where we landed with opportunity. That place has a very special meaning to me. Always will. That would be the place. Yeah, way in the back.
What do you know about how much CO2 is trapped in Martian rocks that at some point in the future has to be released because they are coming in?
Okay. Basically, that comes down to what's the inventory of carbonate rocks on the surface. Carbonate rocks are a lot harder to find on Mars than everybody thought they were going to be. Okay, for years the idea was there was a 4 or 5 bar CO2 atmosphere, dense greenhouse. It all got locked up in limestone, and it's going to be everywhere. Turns out the stuff is really hard to find. I mean, we have found carbonates. We found some wonderful carbonate outcrops with Spirit, and carbonate has been detected from orbit via infrared spectroscopy, but there's not a lot of it. So the total inventory, I wouldn't even want to hazard a guess. I mean, you can make some guesses, as I said, of the water inventory, but boy, trying to get at because there are a number of ways to arrive at that number. Trying to arrive at a total CO2 endowment locked up on Mars is very hard to do. The problem is there are other ways to do a greenhouse. Methane, ammonia, they're great greenhouse gases, so it wasn't necessarily even CO2 that did it. So, man, I don't know. I really, really don't know. Right there. Yep. At what point do you pull the plug on a flagship mission? There's no one-size-fits-all answer to that question. I wish I could give you one. I think the primary criterion that you should use for deciding whether or not to pull the plug on a flagship is your decision process should be forward-looking rather than backward-looking. I think it's a mistake to make a decision on the basis of sunk costs. We've spent so much, therefore, we've spent too much money, we should stop spending money now. Or, I've also seen, we've spent so much, we can't quit now. Okay, I've seen both of those. I think both of those are the wrong way to look at it. What you need to do is look at where are we today? What are the problems? What's required to solve them? Are there unsolvable problems? How much money is it going to take us to get there, and is it worth that additional money to get the job done? Sometimes it is, sometimes it is not, but I think you should make your decision based on work to go and money to be spent instead of basing it on yesterday because yesterday's gone. Yeah.
And the rover that was sent in Spirit, and accomplished what Spirit did on this mission.
Yep.
The mission still made a success, but in fact only about 1/5 or so as successful as this mission actually was. Maybe 1/10 was actually done Spirit. Okay. So that being the case, how does one know that if there wasn't a third rover, that the mission would have been 3 times as successful as this mission? In other words, that Mars is so big and varied that it's quite possible that you still haven't landed in the most important places.
I mean,
Mars,
first of all, I do wish to take issue with your assertion about the relative science and spirit of opportunity. If you had stopped at, say, Sol 1000, compared the two side by side, said who did more science, I would say, yeah, opportunity 3 to 1 5. But if you look at what Spirit accomplished at Comanche, at home plate, the discoveries that were made after we came down off of Husband Hill with that rover, I would stack Spirit and Opportunity just about side by side against each other in terms of their accomplishments. But the good stuff with Spirit came late in the mission. Your point, though, is absolutely correct, and that is we got almost twice as much science by flying 2 as we would have by flying 1. And yet the additional cost of flying the second one did not come anywhere close to doubling the cost of the mission. I think if you flew 5 of them, you'd get 5 times the science. 10 of them, 10 times the science. I mean, at some point, you're going to start seeing the same things over again. But my goodness, you look at what Curiosity has found, nothing like the Spirit and Opportunity science. It's all brand new. Mars is an incredibly complex place with an incredible amount of variety and diversity. You know, I often think of the parable of the blind men and the elephant, right? And one says an elephant's like this, and you know, this is a really complicated elephant. And we've only looked at 2, now 3 spots. There's enormous payoff from going to multiple places on the Martian surface, no question about it. Yeah, right here. Would it be possible to take that rover that I showed you and send it to Mars? Hell no. That thing is so beat up. It's not like, I mean, it's not like a rover, a piece of hardware that you lovingly create and via the same process that you use to send out something off to Mars, and then you place it into bonded stores and you know, armed guards stand watching over it. Oh, this thing is so beat up. I mean, if you actually saw that thing close up, it is scratched, it is bloodied and beaten, and no, you'd never send that to Mars. I wouldn't trust that to go to the Mojave Desert. Yeah?
What do you think the impact of a successful flyby in 2018 that's being proposed? Is that going to be an energizer or not?
If it works, if the funds can be raised, if the mission can be flown, if people can do it and come back alive, I think it's going to be tremendously energizing. I don't think there's any question about it. But you know, every time you conceive of a Mars mission, there are many hurdles ahead, and there are a lot of hurdles ahead for that project. I wish them well. Yeah, way in the back. What's my feeling about methane? This is a tough one. This is a tough one. The best observations of methane have been done via ground-based telescopes. They have looked very interesting. At the same time, they have come under serious challenge by very serious scientists who have poked at those observations and caused people to question whether or not they were valid. It's a very difficult measurement to make. You know, there's methane in the atmosphere of Earth. You got to take that out. There's so many things that you have to take out. The best way to do it is to try what the Europeans are going to do in 2016 and send a spacecraft with a payload that's optimized to answer that question. You know, you can try to sniff it out on the ground. We've tried that with Curiosity, and we haven't found methane yet. But you know, that's just one little spot on the ground, and it's really a global problem. So I think the jury is out, and that 2016 European mission is, I think, going to answer the question. Yeah. Yes.
And if it's a company, the company invests in developing a product and then tries to get the most mileage possible out of that product.
Right.
So why is it that the federal government doesn't employ the same technique? Like, take the design that you spent a great amount of money and time developing, and maybe a dozen of them now. It's so successful, it's been flight proven.
You know,
I said there's so much more science that could be done if you had more of these.
I think the obvious answer is that the motivation behind the NASA enterprise is different from the motivation behind a private company. Okay? NASA is an organization that since its inception has always been about doing the next thing that's new, the next thing that's different, and coming up with something, you know, dramatically new. And you know, frankly, I'm thrilled to see that the 2020 rover looks just like Curiosity with the same entry, descent, and landing system. We're going to fly the Sky Crane again. We know that it works, and we're going to use it. So maybe some of these lessons are being learned. Honestly, if you tried to build Spirit and Opportunity again today, you couldn't do it. We couldn't even get the parts. You know, the avionics particularly is just completely changed. Yeah.
What's your most favorite surprise found on Mars? I don't think it's perchlorate, right? But what might be the thing that you would...
Oh, my favorite surprise. Wow. That's a hard one because there have been so many. You know, I mean, there have been a few that were just sort of laugh out loud crazy when the first time we found an iron meteorite, I was just stunned. You know, I was just absolutely stunned. I mean, we had gone to investigate our heat shield, which had, you know, fallen off the vehicle and crashed on the surface. And we drive up to the heat shield, and right next to it, there's this shiny metal thing, and it's an iron meteorite, just sitting there. I mean, I told the team we shouldn't stand here. This is obviously a place where big metal objects fall from the sky. But you know, I was just stunned when we saw it. And now it's like, another meteorite, let's go. Because we found so many of them. Man, the first time we saw a dust devil dancing across, I mean, we knew those were there. We knew meteorites had to be there too. The Silica Valley, that was a big one. I was stunned by that one. 91% pure silica just popped out of nowhere. It's hard for me to pick. I mean, there are some that are tremendous scientific discoveries, and then there's other ones where you just go, holy moly, a meteorite, you know. So, hard to pick. Yeah?
What role historically have advocacy groups like the Mars Society played in your experience in getting your mission done? And looking forward, what can groups like this do?
The most important thing is keep the pressure on. Okay? Advocacy groups are not going to, for the most part, raise the funds that are necessary to do these multi-billion-dollar enterprises. That's not what it's about. But what advocacy groups do is they are a constant source of pressure, an unrelenting source of pressure on decision makers saying, yeah, this is important. Yeah, remember, this is important. Oh, don't forget, this is important. And you just can never let up. You can never, ever, ever let up. Okay? And as soon as you let up, people forget. And they go on to the next thing. But if there's this constant drumbeat out there, we care about this, we care about this, people care about this, it makes an enormous difference. And, you know, the number of people who are willing to come to a conference like this and pay to attend, and you're the tip of the spear. Okay, but there's an enormous body of people out there who are fascinated by Mars exploration, who, you know, they don't go to the effort of being members of the Mars Society, but they still really care. And you're amazed at how small a number of letters say to Congress, how much of a difference it. I remember one time I was talking, this wasn't that many years ago, or there was some NASA program that I was trying to advocate, and I was visiting some members of Congress and talking to their staffers, and one of the staffers said, oh yeah, we've been getting a lot of letters on that one. And I said, just out of curiosity, this is one particular congressional district, how many letters have you gotten? He said, oh, I think we've gotten 5 or 6 letters. And I go, 5 or 6? And he said, well, yeah, we subscribe to the cockroach theory. If you see 5 or 6 of them in your kitchen, there's a lot of them back in the walls. Okay? So, you matter more than you think you do. You really do, and just keeping that pressure on, it's tremendously important. Yes? Do I think we'll see humans on Mars in my lifetime? I don't run anymore, but I cycle a lot. I swim. I watch my cholesterol. I've been trying real hard to watch what I eat, keep my blood pressure down. Going to D.C. doesn't help with that. I think it could. I'm 57 years old. My dad's 86. He's doing well. 29 years. Yeah, we can be on Mars. Okay, what are the criteria for what samples to gather? Well, obviously you're looking for diversity, but the primary criterion that's going to be used for selecting the site and selecting the samples is maximizing the probability that they will preserve evidence of biology or prebiotic chemistry. Okay, so you're going to be looking for places where there was water, and then you're going to be looking for either very fine grained sediments or precipitated minerals, because those are the kinds of materials that best preserve primitive organic matter. And so, yeah, those are going to be the primary criteria. Is maximizing the preservation potential for evidence of life. Yeah.
Geology, and you get eventually to a point where you do start drilling, and you're doing the geology and then getting to the biology together?
Oh, yeah. I mean, the question had to do with getting beyond surface geology and getting below the surface. I think that's tremendously important. I think it's one of the most important things that we can do. In fact, Robert and I were talking about this over dinner, is, how deep do you have to drill to find liquid water? It's a very complicated question. It has to do with the chemistry of the water, what salts are dissolved in it, so what's the freezing point, what's the geothermal heat flux, it's going to vary a lot from place to place. And so I think one of the primary objectives for geologic exploration would be to locate the places that are the best ones to drill. And then, drill baby drill. Radar is certainly one tool that you can use. Ground penetrating radar is tough on Mars, as it turns out, because the Martian subsurface is very geometrically complicated. A lot of it is impact-generated regolith into those big boulders and chunks of stuff. And so what you would like to see be a nice, clean radar signal going down and coming back. You get a lot of reflections and refractions, and it's pretty messy. But radar is certainly one thing to use. Any measurements that you can make of heat flow and how it varies from place to place are going to be valuable. Certainly, we talked about methane, okay? There are hints from these controversial Earth-based methane observations that there are specific source regions for methane on the Martian surface. If that turns out to be correct based on what we see from that European mission in 2016, those source regions would be particularly valuable places to go and drill, I think. Yeah. I think that orbiters and rovers, you need to have both at the same time. Certainly, we have found that orbiters can play a very important tactical role in helping to make decisions in real time. I don't think I'm giving away too many secrets here. We just recently asked the HiRISE instrument on the Mars Reconnaissance Orbiter to do some special observations for us of infrared spectroscopy at Solander Point, which is this place that we're just climbing up to. That picture that I showed you is from Solander Point, with opportunity as a way to help guide us to where we think there might be clay minerals. This is an observation they just did for us in the last few weeks. So operations, besides the obvious point that orbiters provide data relay capability for the assets on the surface, having assets in orbit that can do specific observations in support of surface measurements is tremendously valuable. So I think you want to fly both at the same time. Yeah. I'll warn you, by the way, I can do this all night. So go ahead. Okay, the worst message you could take away from the longevity of the MER rovers is that somehow we figured things out. Okay, to a certain extent, we've gotten lucky. We used incredibly primitive technology on our rovers. We did not, the only new technology on those vehicles really is in the software. The hardware is all tried and true, tested stuff. We've gotten lucky with the weather. We've gotten lucky with a bunch of things. Mars is hard, and it's going to stay hard. And I think it would be a mistake to draw any lessons from opportunity and Spirit's longevity other than over-design and test and test and test and test and test. Yeah. What do I know about the capabilities of the Chinese in this area? Not a whole lot, to be honest with you. They have expressed an interest in doing things like rovers on the moon and Mars. I remember seeing in the aerospace media a picture of a proposed Chinese rover. And if imitation is the sincerest form of flattery, we were very flattered by the design of their vehicle. It was interestingly, though, I think, for the moon. But anyway, to be honest, I don't know about their capabilities for robotic surface missions anywhere. They are in the process of developing some very significant capabilities for human space flight in low Earth orbit. Okay, with their missions to their space station, they're flying, they've joined the family of nations that can go it alone and do orbital space flight. And there aren't too many of those. So they're serious and they're getting better. They're climbing that learning curve real fast. So I would not sell the Chinese short at all. They're going to do a lot. Yeah. There are many. There are many, many things. And those of us who are so fortunate as to be able to be entrusted with hundreds of millions, billions of dollars of taxpayer money need to take this issue very, 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 very seriously. Okay? When we launched our vehicles, the mission had cost $800 million, didn't know if it was going to work or not, and we expected to put 2 rovers on the surface for 90 days each, total of 188 days. You do the math, that worked out to $4.5 million a day. I drilled that number into my team's head. I wanted everybody scared. I wanted everybody coming into JPL every day thinking, holy moly, we got to do $4.5 million worth of science today. Well, let me just finish with this, because this is an important point, okay? We're not doing this for fun. We're not doing this just because we like to send rovers to Mars. The missions that we fly had better be worth it to the taxpayers, or we don't deserve to fly them. And that applies to human missions to Mars, it applies to the Hubble Space Telescope, it applies to anything that we do in space. Now, what are we getting for our $800 million on MER? I feel like what we're doing is making progress towards answering basic questions like, are we alone in the universe, and how did life first arise? I sleep okay at night, having spent $800, $900 now $1 million on these things. But it's for all of us who are advocates of Mars exploration, this is a question we all better be really ready to answer when we're asked. Because if it ain't worth the money to the people who are paying for it, it shouldn't happen. Go ahead.
One last goal. Is there a goal?
Is there a goal? For Mars exploration or more broadly? For Mars exploration, I would say that the goal, first and foremost, is to I'll give you 2 goals. One is to determine whether or not life ever took hold independently on another world. Because if it happened twice in just this solar system, then it takes no great leap of logic, imagination, faith, or anything else to believe that it could be commonplace throughout the universe. Second scientific goal for the exploration of Mars is, let's suppose that happened. Let's suppose that miracle of the origin of life did take place on Mars. Now, it happened on Earth, we know that because here we are. But it happened early in the Earth's history, and the problem is Earth has been so active throughout its history that evidence of that event is forever gone. The Earth's tectonic and volcanic history have completely destroyed evidence of the origin of life. We can never find that evidence. It's gone for good. Mars is covered with 4 to 4.5 billion-year-old rocks. So if life did take hold on Mars, not only could we perhaps discover that fact, but we might even find out how it happened. That story still written in stone on the surface of Mars. And to me, scientifically, that makes it worth the effort. Yeah?
Speaking of possible life on Mars, do you have any knowledge of why the alleged crinoid-type fossil that was imaged by one of the rovers was apparently brown?
You know, I wish it had been a crinoid. I really, really do. I live in upstate New York where there are lots and lots of Devonian rocks, 350 million-year-old rocks with lots of crinoid fossils in them. And the particular thing that you're referring to doesn't look anything like a crinoid or like anything else that appears to be a fossil. It's probably some coarse-grained mineral crystals. Honestly, once we had looked at it with every spectrometer that we had, once we had looked at it with our microscopes, we had nothing left we could do except see what was underneath it. So that's what we did. The images exist, all the data exists. We did grind it away, and that was my decision. It was the right thing to do. Yeah? I would say that the report that you're referring to has not had a deeper penetrating effect or a chilling effect on NASA's desire to explore. I think that NASA feels that its mandate is to explore the solar system, and it's taken that seriously and doing the best that it can, period, full stop. Okay. Yeah. Oh, so would we withhold the data? Okay. No, that's a good question. That's a good question. You know, on our mission, we made the decision very early on that we were going to pipeline our data, everything, straight to the World Wide Web, untouched by human hands. We still do that to this day. So, you know, this audience probably knows this already, but one of the things that I love to do when I give talks like this is I put up images like I just put up, and I say, and this just came down from Mars a few hours ago, and everybody goes, ooh, like I tapped into some secret NASA database. No, I just download it from the same website that everybody else does. But there was never on our mission any discussion at all, ever, of withholding any data from being sent down right away, with a single exception. There was one exception very early in the mission, okay? And that was that on the back of the high gain antenna, there was a memorial plaque for the Columbia crew. And we wanted to get that image down and get it beautifully processed and make sure it was okay with the families of the Columbia astronauts before we released it. Those are the only images in 3,400 sols that we ever held back. Everything else just goes straight to the web, and if there's a giraffe running through the scene, you'll see it when I do. Three more questions. Okay, one right here. Whoa. You're asking me to give away too many secrets here. I got a few ideas. The question is, what would be like the top thing that you would want to do now from orbit on Mars, given the current state of things? You know, I'll just say flat out, I think one of the main things would be to do really, really high spatial resolution, very high signal-to-noise ratio infrared spectroscopy. That would be at the top of my list. Two more, right here.
When I see if we use the in situ fuel production?
In situ propellant
So we
production.
can come
Yeah.
up with that.
In situ propellant production has been one concept that has been talked about. There is not currently a sufficiently robust, sufficiently well-developed capacity for in situ propellant production that a hard-nosed project manager or a hard-nosed NASA manager would be willing to risk a $10 billion mission on. And so, you know, there are better ways to do everything that we do, okay?
Was they're willing to do in-orbit docking and passing the...
Those are all things we know how to do. Those are all things that we actually have experience with in spaceflight. So we tend to take a very, very conservative approach.
production is something we did 150 years ago.
Well, if it is possible to demonstrate with sufficient robustness the ability to do that, and in so doing increase the reliability and lower the cost of sample return, it'll happen. So far, it hasn't taken place to my satisfaction. One more, last one, right here. My personal opinion, are we going to find life on Mars? That's a great question to end on. Okay, I will give you my answer, and I want to make a specific point with this. I don't know. But I want to make a very important point here. One of the biggest mistakes that you can make when you're a scientist or an explorer is to wish for an answer. One of the saying that I've heard scientists use is, I wouldn't have seen it if I hadn't believed it. Okay? You don't want to fall into that trap. And so my view has always been that rather than guessing whether or not there's life on Mars, rather than wishing for there to have been life on Mars, I just want to keep an open mind and build a better experiment. Thank you.
Including Chris Nye, Abshet Kuman, Kristen Bebo, Shannon Floyd, Kiera Fortier, Brian Guzman, Krista Puga, Nick Smith, Kai Statz, Josh Nelson, Emily Jennings Fast, Hope Jennings, and Mandy Morris. And I also, by the way, want to thank my machinist at the company, James Kilgore, who made this trophy for Steve Squyres. Okay. He also made the trophy last year for Elon Musk. So he really puts a lot of love into it. He believes in Mars exploration and uses his skill to send that message. Now, okay. The Mars Society was founded 15 years ago in this room. This is where our founding convention was, right here. And so it's useful to look back at what we said then and what we've accomplished since and what we hope to accomplish now. Okay. When we had the founding convention, we said we'd do three things. One was broad public outreach to spread the vision as widely as possible. Second was political work to further the government-funded Mars exploration programs, both robotic and human, in both here and in Europe, anywhere else. And the third is projects of our own. Okay. Now, some of these things, especially in the first two categories, are hard to quantify because you cannot see directly the effects of spreading the vision or even of your political work. You can see political outcomes. You don't know how much of it you were responsible for, how much others were, but you can see the outcomes. But what have we done? Okay, starting with the most concrete, the things that we can quantify, we built the Flashline Mars Arctic Research Station, and we built the Mars Desert Research Station, and we operated them now for more than a decade. We've had 11 crews in the Flashline Station and over 130 crews in the Desert Station, 6 people each. That's over 800 people have had the chance to be a member of a crew of one station or another, of one crew or another. We've learned a lot from this. They've learned a lot from this. People who participate in these crews come out with at least some real intuition as to what a Mars mission is likely to be like, and if they then go on professionally, some of them are already engaged in professions relating to space exploration. Some never will. Some are students, many are students, who subsequently will end up at NASA or Lockheed Martin or at a university where they may be working on things, and this will make their contributions much more valuable. And of course, there's been press coverage of these stations. Okay, they have been covered in the New York Times and in CNN and the Discovery Channel and the BBC and Russian national television and Japanese national television and Chinese national television. Okay, that is, collectively, billions of people have gotten a chance to see the idea of human exploration on the surface of Mars made sensuous by the coverage of this activity. And we intend to make this a lot more sensuous with the Mars Arctic 365 mission, which we're now gearing up to do, which will be the first full-dress Mars mission. But we'll come back to that, because I'm sticking right now with what we have done rather than what we intend to do. There is the political work. We, at the founding convention, we set basically 3 primary political goals. Okay, 2 related to the robotic program. Okay, we wanted a doubling of funding of the JPL Robotic Mars Exploration Robotic Program, which was then funded in the neighborhood of $250 million a year. We said that needed to be doubled. We also said that we needed to have what we called a Mars Discovery Program. The NASA had set up under Golden a program called Discovery, in which teams could freely compete mission plans, and so that PI-based teams at universities in particular, okay, usually with some industry participation, but generally university-led, could propose their own creative, innovative ideas for a space mission, and then these would be competed on the basis of scientific return, technical credibility of the design, and cost, and may the best thing win. And so the Discovery Program was launched, but it became clear that the Discovery Program was essentially tilted or rigged, if you will, that Mars missions would not be selected for it because it was considered Mars had its own program, and so things like the Near-Earth Asteroid Probe or the probe to collect space dust or something, that these things would be, and that's all fine, but we said, okay, give us a Mars Discovery Program, okay, so that you'd have, in addition to this well-organized, very planned program coming out of the Central Committee at JPL, you would have these wild cards of other ideas that would be able to enter into the mix, okay? And then the third was to try to get a Humans to Mars program initiated, because, just as Steve said just now, NASA needs a goal. The goal needs to be humans to Mars, okay? You can't just have a human spaceflight program without a goal. It doesn't make any sense. And it certainly won't get us to Mars if it doesn't have that goal. So that's what we said there. Now, we had allies on those things, but so it's hard to apportion the credit, but the robotic spaceflight program, the JPL, the program of which, for instance, the MER rovers were a part, was doubled. It was increased to over $500 million, and that made missions like MER and the Mars Odyssey and the Mars Reconnaissance Orbiter and Curiosity possible. Okay? The Mars Discovery Program, which I think we do have a right to claim credit for because it was an original idea with us, was in fact executed. And 2 missions, well, 1 mission has been flown, that was Phoenix, okay, led by Peter Smith, who was in fact a steering committee member of the Mars Society, and that was a very successful mission. And the second mission is Maven, which we heard about today, and that is going to be launched this November. So that's a real accomplishment. And then we also had another important political accomplishment along the way, which came sort of unplanned, which was we managed to beat the crap out of Sean O'Keefe on his decision to abandon the Hubble Space Telescope, because we were not going to have the Bush Back to the Moon, Onto Mars initiative branded with the mark of Cain that, yeah, sure, give us the Moon and Mars and can junk Hubble. What do we care about Hubble? No, okay? And also, in particular, that it was a crime against science. And furthermore, a space agency that said it wasn't going to go Hubble because it was too dangerous would certainly never be capable of sending humans to the Moon or Mars. Okay? So we entered that fight. It was kind of unexpected that we would take such a strong stand on that, but we did, and we won. Okay. Now, then we had some input into the decision for the Bush, what it was called, the Vision for Space Exploration, although Mars was put in 3rd place after business as usual in the Moon on that, but nevertheless it was sort of there. But I would have to say that overall our success there has been limited, except in a broad brush term, which is that now, I mean, the Obama administration is saying that the long-term goal is humans to Mars. Now, unfortunately, they've embraced that as a vision rather than as a program, okay? And there's a difference. There's a difference between saying this is kind of where we have to go, as opposed to we're doing this, here's the plan, here's the funds, let's do it, okay? But still, there is some progress there, okay? Because at the time we were founded in 1998, okay, the Clinton administration had even put out a whatever it's called, some kind of space policy document that explicitly rejected earlier Reagan-esque language that talked about human exploration of the solar system as being just that's like manifest destiny. We're not into that. There's we don't know about doing anything like that. So at least now there's a sort of a verbal commitment. We've accomplished something there. Then there's spreading the vision, and this is the most tenuous of all in terms of figuring out what you've accomplished and what you haven't, because you're dealing in the realm of ideas, but yet while it is the most difficult to track, it is potentially by far the most powerful, okay? That is, it is ideas that make history. Ideas inspire people. And they turn those people into actors for those ideas. Right now, some of the most promising things we're seeing in space is coming from these zillionaires who all of a sudden have decided to commit themselves to do something important to make humans to Mars happen. Elon Musk, Dennis Tito, so forth. Okay, well, where's this coming from? Somehow they got these ideas in their head. Okay, Tito here was quite explicit. Okay, he read the case for Mars, this, that. Okay, Musk, it's less clear, but for me, myself, reading Arthur Clarke, Robert Heinlein, these people put these ideas in my head, and that's why I'm doing what I'm doing. Okay, to the extent we spread these ideas, you never know where they're going to end up. You never know whose souls they will take hold of. Some of these people can end up being congressmen or presidents. Some of them can end up being billionaires and initiating programs. The work we do in spreading this vision and shaping the intellectual atmosphere, that has a role in both causing political outcomes and also causing individuals, sports of nature as it appears, to do things. And by the way, this is why we're ultimately going to win. Let me tell you, we are going to win, and I will tell you exactly why it's, well, there's nothing certain. There could be World War III, civilization could collapse, and then we won't win. But no, I mean, that can happen. There have been times when society has gone off the rails and great dreams were taken down with it. But assuming that the world continues to progress more or less as it has done since the end of World War II, okay, why can we say we're going to win? Well, I'll tell you why. Okay? Because in 1957, when Sputnik flew, the average GDP per capita in the world was $2,200 in today's money. And today it is $9,000. Okay? And the population of the world has tripled in that time. So the GDP per capita has quadrupled, the population has tripled. That means the total GDP of the world has gone up 12 times, okay, since beep beep. Okay? Now, okay, furthermore, okay, if you think about the population of the world as a distribution, a Gaussian distribution or Maxwellian distribution or whatever, okay, if you have the average here, then you have a sort of a tail of it out here. In other words, if the average income is $9,000, then there's a certain number who are making $40,000 and a certain number who are making $40 million and so forth. And as the average shifts, okay, in this way, the numbers out here in this upper part of the spectrum, okay, greatly increases. Okay, 100 years ago, there were maybe 3 people in the United States as rich as Elon Musk: J.P. Morgan, Rockefeller, and Harriman. Okay, that's about it. Okay, now there's probably several hundred. Okay, and similarly around the world. So, as the number of such people increases, you have increased probability that there will be unusual ones that decide to make this their preoccupation. Okay? And then especially if the idea is being made more and more current and convincing a larger fraction of the people, you will have more and more. So look, Musk is out there doing SpaceX, and he may or may not success in building this thing up and sending people to Mars. Dennis Tito may or may not be successful in making Inspiration Mars happen. But these sorts of things are going to happen with increased frequency because of this. In other words, where there is now 2 or 3 of these people active in the United States today, 20 years from now, there will be 50 such people doing this kind of stuff. Okay? And the probability of success, at some point, we're going to break through. Okay? At some point, we're going to break through. So we have to continue to do what we're doing. Now, the immediate project that we have in front of us is this Mars Arctic 365 mission. Now, this is the first full dress rehearsal of a human Mars mission that anybody has ever done. Now, we're going to have a crew up there in the Arctic, in this polar desert, okay, attempting to conduct a sustained program of field exploration, geology, microbiology, climatology, so forth. Exactly the same thing you'd want to have the scientists, astronauts do on Mars. They're going to do up there, and they're going to do it within the same constraints as a crew would do on Mars. They won't be able to go outside without wearing spacesuits. They're going to have to do their lab work. They're going to have to engage in a telescience collaboration with our remote science team in the United States. They're going to have to tend to the repair of equipment. Okay, they're going to have to deal with real life. They're going to have to attend to the chores of daily life. They're going to have to get along with each other under those conditions. Now, compare that, for example, to Mars 500. Now, Mars 500, to me, is very interesting, okay, for the following reason. that it got such worldwide press attention, despite the fact that it was nothing but a small group of people sitting in a room in Moscow for a year and a half. Now, let me tell you, they've had small groups of people sitting in rooms in Moscow for up to 10 years at a time, okay, okay, or even longer, okay? There's real heritage there. Now, and under considerably tougher conditions than the Mars 500 crew had to put up with, okay, and okay, okay, they proved Russians are tough, and well, actually, they proved people are tough, and but nevertheless, okay, despite the limitations of that mission sim, it got worldwide attention. People around the world are they're looking for anything that is moving the ball down the field towards humans to Mars. So, I mean, there was some things they learned there, so it was worthy of coverage without question. But compare that to this, okay? I think we're going to rivet the attention of the world with this thing, really. And, I mean, this is both Mars exploration and a real adventure. This is really going to drive things. I think we're going to wake people up. This has really the potential of waking up millions of people. This is the attention of really focusing NASA to say, look, this is where we should be going. This is what we should be trying to do. And I would be delighted, by the way, if NASA took this to heart and then put up their own much fancier Mars Arctic Research Station up there and started doing one-year sims that outclass ours, because really, the most important thing about this vis-a-vis science are not our own results, but what we can do to open up a new field of scientific investigation. It's kind of like Galileo and his telescope. Well, he actually made some important findings, but what's even more important was he opened up the field of telescopic astronomy. He demonstrated the validity of a new instrument, okay, for conducting a certain kind of science. We're about to demonstrate the validity, the usefulness of a new kind of instrument for studying human Mars operations. So this is what we intend to do. It is a grand project, but it's going to cost money. This stuff isn't done for free. So I have to ask people here to pitch in. Okay, you know, if you want something to happen, it's your responsibility to help make it happen. And I know many of you are very active on other fronts. You're doing outreach, you're doing other things, and that's very important. But it also takes money, okay? So I'm going to ask people here to help. I want to ask who here in the audience is willing to give $1,000 right now. I will. Okay, Mark Arnold over here. Who else? Anyone else? $1,000 bucks. Is someone over there in the middle? Oh, right over there. Okay, over here, a third person. Who else? Anyone else? Over there in the back. Okay, fourth. Anyone else? Come on, let's get to 10. Come on. Who else? Okay, $500. Who's willing to give $500? There's one over here. And over there. Who else? Over there. Who else? $500. It's the cost of an airline ticket to someplace you never really wanted to go. Over there. Okay. Who else? $500. Over here, right there. Who else? $500. Who here can give $500? All right. $250. In the back, there's one. There's another one over here. Right here, in the front, please. Nicole, somebody, wake up. Oh, he's gone. Okay, who else? $250. Over there in the back. Who else? $250. There's a gentleman over here. Okay. Who else? $250. It's half the price of an airplane ticket to someplace you don't want to go. Come on, $250. Who can do it? All right, $100. All right, right here. Okay, over there. Over there. Come on. Everybody. Let's do $100. Come on. Get everybody here. Do $100. Come on. Over there. Another one. $100. Who else? Over here. $100. Anybody at this table for $100? Come on. There's one right there. Okay. $100. Over here. Come on. $100. Anyone else over there? $100. All right. Well, that's great. Thanks. But we're not done because there's some things you can buy. Okay. Right. Now, let's start with actual evidence of Arctic megafauna. Okay. You know how valuable this would be if we found this on Mars? But these scientists go nuts. They got to the heat shield and they found claw marks on it. Okay, here it is. This was retrieved from the Arctic by Joe Palea. Okay, these are not mere holes. These are polar bear artifacts. Okay, so, what? Pulse bear. That's what they are. So let's start the bidding on this one at $25. 25. Okay, what? $40. 50. 60. Come on. This is worth a lot more than $60. Come on, $60. Who? Anyone for 65? You're gonna let this go to this guy? What? Okay, $60. You're gonna let this. What? Who's got $100? $100. You're gonna let him beat you? This bloody American. What? All right. Sold for $100. Someone asked a question about crinoids on Mars. Okay. This is a Devonian coral found near Flashline Arctic Research Station. This is real. NASA will never be able to cover this up. This is actual proof of life on Earth. Definitive. It's real. Okay, absolutely real. Nobody with their touch-up cameras hide the evidence. Okay, do I have $25 for this? $25. $25. 30. Anybody for 30? Look, this would cost a lot more than that in a rock shop, for crying out loud. 25? Is we hear 30? I got 40. 40 over there. 45 anywhere? 45? 45. 45 over there. Anyone for 50? This was found by Joe Palea himself. Yeah. He'll sign it for you. Okay, so we have, what was the bid? 45? Okay, sold, what, sir? 60. Now, there's something. 65? What? Sold for $60. Okay, and now for the final auction item, we have a Martian flag. But this is not just any Martian flag. This was the flag flown at Flashline Station this year by the Mars Arctic 365 Phase 1 mission. And it is signed by the 3 members of the spearhead, Joe Palea, Justin Sumter, and Adam Nair. Okay, now, so this is a historic flag. This is the flag we brought up when we revived Flashline Station, which we had not been to for 4 years, okay, and put it back online. And by the way, it's amazing, because we weren't sure this station would be in any kind of shape at all. We thought the windows might be busted, the generators were, they got the old generators working that hadn't been used in 4 years. They were brought up in 2001, okay. The comm system, okay, it works. Anyway, there's all kinds of stuff they did. Joe told you most of it, but they actually did more than that. But here's the flag. And, you know, this is a great flag. I commented on it a little bit yesterday. But, you know, red, green, blue, red Mars, blue Mars, red, the desert Mars that exists, green, the life that could transform it, blue, the fully living blue planet it could become. And more than that, simply a statement that it is a new flag, that there will be new nations, okay, that we are living not at the end of history, but at the beginning of history. And, you know, if you go to the Mars Society website right now and you see the picture of the Mars Arctic Research Station and a flag next to it, this is that flag. So, do I hear $100? $100. $100. Do I hear 110? 110. 110 over there. 120. Come on. Jesus. It's 110. Anyone for 120?
120.
120 right here.
Can I trade in my piece of plastic?
They go great together, that plastic. They are a matching set. Okay, we're up to 120. Come on. This is something. You can fly this on Memorial Day. Okay. Do I hear more than 120? 150. Now that's something. Okay, how about 200? I mean, this is the real thing. You know, okay, the first flag that we flew at Flashline Station went for $4,000. That's a fact. If you were at Stanford, you would have seen that also. Okay, but this one is for the revival of Flashline Station. So we got 150. Anything more? Then sold for $150. Okay.
I'd like to issue a challenge. I'll increase my $500 donation to $1,000, but I need 2 of the people who also donated $500 to increase their donations to $1,000. Come on, who's going to be first? It means a lot to the Mars Society. There were a lot of you out there.
Just think about it. If you then increase your bid by 500, you'll be netting the Mars Society 1,500. This is triple money.
Good move. There's one.
There's one.
All right.
One more. One more. Come on. Triple the money. You give 500, we get 1,500. It's tax deductible. You can even try deducting 1,500. Listen, think about this for a minute. How many people here are upset about the NSA spying program? Okay, raise your hand. Come on, I don't like it. I think it sucks, right? They should not be spending money on that. If you do a tax-deductible donation, that money comes right out of the NSA's pocket. So this is for freedom. Come on. Is there one other person? Is there one honest person in Gomorrah?
Not happening without you.
Or 5 people who gave 200 each, gave 100 each, adding 100 to their bid.
I'll do that.
Okay, there's 100 who made himself too. So we need $400 more. Come on. Anyone else? $100. It's like the cost of going skiing. And then it snows and you don't even get to go skiing. What? Another one here. That's the second. We need 300 more. Another one there. That's Gene Hunter. Okay. So we need 200 more bucks here. Do you want to add? No. Okay. Come on. $200. One over there. That's another 100. We need 100 more. 100 more. This $100 is multiplied 15 times. There it is. Joe Pillay. Okay, the challenge has been met. Okay, that concludes tonight's banquet. I'd like to thank you all. See you here tomorrow morning at 9.